I bring you physics from Park City. Here's hoping this works. I have my iPad propped on a lamp, held in place by the illustrated book of Harry Potter and the Sorcerer's Stone. I wanted to, the whole point of this circus is that I wanted to bring you a couple of example problems. Two about the work done by friction, particularly including inclined planes, because we still, and it's totally normal to still struggle with forces decomposed into the inclined plane tilted axes. And then a couple of example problems for power. This is probably gonna have to be two separate videos for the two types of example problems. So I wanted to show you problems 48 and 51 of chapter 6 for work done by friction, and then 57 and 60 of chapter 6 for power. So start with 48. A ski starts from rest and slides down a 28-degree incline, 85 meters long. If the coefficient of friction is 0.090, what is the ski's speed at the base of the incline? Then B, if the snow level at the foot of the incline, if the snow is level at the foot of the incline and has the same coefficient of friction, how far will the ski travel along the level? So we have two sections of motion. We have sliding down the plane, and then we have sliding across a horizontal / level section, so A and B. We have a coefficient, here let's start here actually, we have an incline of 28 degrees. We have a coefficient of friction. It's not stated whether it's kinetic or static, but we know the ski is sliding, so we can confidently call it kinetic friction. The length of the plane is 85, why am I writing it as a point? 85 meters long. So from start of sliding to end of sliding on the hill section, 85 meters in length. Angle of incline 28 degrees, coefficient of kinetic friction 0.09. We do not know the mass of the ski, but we're getting used to the idea that if we have no springs involved, we do not need to know the mass. The mass is factorable for conservation of energy. So again, the first part of the question is, what's the ski's speed at the base of the incline? And so that's asking for velocity. That makes me think of kinetic energy. If I could talk about the kinetic energy of the ski at the bottom, then I could compare it to the gravitational potential energy at the top, and the difference in energy will be made up for by the work done by friction. We could absolutely have done this problem in the last unit by finding the force of kinetic friction versus the component of gravity pulling the ski down the hill. We could have found the net force on the ski. We could have calculated the acceleration of the ski using Newton's second law and then applied kinematics to find the speed at the base. As you're finding, there are two ways to approach these problems usually if the force is constant. We can consider constant and conservative. If we can consider either conservation of energy, or we can consider Newton's second law and kinematics. So I want to consider the energy of the ski at the top of the hill. Here's part 1 or point 1, and here's point 2, versus energy at the bottom of the hill. There are no springs, so I can leave U sub S out of the equations. And I consider, oops, that should be a 2. I consider the kinetic energy at the top and the gravitational potential energy at the top versus the kinetic energy at the bottom and the gravitational potential energy at the bottom. These two are not going to be equal to each other if I only consider kinetic and potential energy, because there is work done by friction as the ski slides down the hill. So I need to consider the kinetic energy at the top, the gravitational potential energy at the top, the work done by friction, the kinetic energy at the bottom, and the gravitational potential energy at the bottom. Now I have a complete model for the motion of this ski. So at the top, it's at rest. Kinetic energy is 0. At the bottom, it's as low as it goes. So I'm going to say y equals 0 at the bottom. And gravitational potential energy is 0. mg y. is equal to, I'll leave it as WF plus half V2 squared, and it's that V2 that I'm trying to find. So I'm getting there. Now I need to decode work done by friction. The work done by friction is equal to the force of kinetic friction times the distance it slides down the hill. Force of kinetic friction is the normal force, mu sub k times the normal force, times distance, of course. And so then the normal force here, because we're on an incline, is equal to the component of the pull of gravity that's in our new y direction. So now I have to go back to my free body diagram idea. I have a normal force pointing perpendicular to the hill. I have a pull of gravity straight down. I have a component of pull of gravity that we have been calling FGY, that is into the hill, and I have a component of pull of gravity, FGX, that is down the hill. You'll notice here that I don't actually need to know anything about FGX. For my energy approach, I'm considering gravitational potential energy, kinetic energy, and work done by friction. My angle of incline is equal to the angle between the y component of pull of gravity and the directly downward part of gravity, directly downward pull of gravity, I should say. And now I can complete my substitutions into the equation. So again, I'm considering the force of friction, and I know that's mu sub k times normal force. I can now decode that to be mu sub k times mg times cosine of 28 degrees, because the y component of pull of gravity is adjacent to my known 28-degree angle. Substituting back in now, I have mgy equal to work done by friction, mu sub k times mg cosine 28 times distance the ski slides down the hill plus half mv squared at the bottom of the hill. I have a little more decoding to do because I know that the hill is a length of 85 meters, but I don't know how high the hill is. Now I consider this hill triangle 28 degrees, 85 meters, and I want to know this y. So the y is the side opposite the hill, and so I know that sine of 28 degrees needs to be opposite divided by hypotenuse. So y is equal to 85 sine of 28. And now I can finally solve. mg times 85 sine of 28 is equal to coefficient of kinetic friction, mg cosine of 28 times the distance, that's 85, actually I could just put that in, 85 times half mv squared at point 2. I have mass in each of these terms, so I can factor it out. I'll clean it up a little bit. That was a plus. And finally, I would solve for V2. G is 9.8. 9.8. Mu sub k is 0.09. And I'm solving for V2 squared. Well, V2 in the end. And I'll leave the algebra to you because I am running quite out of time.